This is the Amp Hour Podcast, released July 15th, 2018. Episode 399. An interview with Steve Kreuzer. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Steve Kreuzer of Exponent Consulting and Engineering.
Welcome, Steve Kreuzer, former roommate and high school buddy and college buddy and person who entered the same industry I did.
How you doing, Chris?
Good, man. It's been too long. It's been too long.
It has. No matter how long it's been too long. Exactly.
So I've known Steve since the first day he showed up in third grade, Smallwood Elementary School. We hung out, and he lived up the street from me. And ever since then, we've been like in parallel paths towards the same industry, at least. Yeah, so that's been pretty crazy.
It has. I don't think there's anybody else who has lived in the same quantity of places that I've lived in at the same time.
Right. Exactly. Right. But you ended up on the other side of the coin a little bit. You are a PhD in mechanical engineering, definitely further than I decided to go, and also mechanical. So kudos on both those things.
Oh, thank you.
Yeah. I mean, so how did we get here? What is your background story? Since I'm only just telling you the part I was part of.
Absolutely. Yeah. So after leaving Buffalo, we both went to Case Western and there got into the mechanical engineering line of study. A lot of that came from just my background at home, working a lot of sort of construction and remodeling stuff with my dad and family members, and just kind of doing odd sort of mechanical type stuff around the house and elsewhere. But after studying at Case in mechanical, got involved, actually was looking for research opportunities just to try out what grad school would be like. Got hooked up with a lab down in North Carolina at Duke doing biomechanics type stuff. And that really, boggled my mind, the idea that biology could be controlled by mechanics, which was, something that was abstract in my classes at the time, but really took on a really concrete meaning in an interesting way when I started looking at cartilage and some musculoskeletal mechanics type stuff. So that got me interested in the biomechanics realm. And then I decided I wanted to go to grad school based on those experiences. Also did a co-op working on dishwashers, which in contrast to cartilage and whatnot was, So it was down in Kentucky, which was a lot of fun. Went to the Derby, all that sort of good stuff, but didn't end up really stoking my interest all that much.
It's surprising. Who doesn't like a good dishwasher? Right. That's a good thing, though. GE has since sold that division, right? They're now a Chinese industry.
They are, and that was after they had a huge fire that burned down one of 6 warehouses, I think, in that location. So, it was kind of interesting. It was a nice introduction, I guess, to sort of corporate America. But what it taught me was even though I was in their sort of research and development wing, where they were doing sort of this is an embarrassment to the term to call it this, but their sort of skunk works type approach to dishwashers and refrigerators and stuff.
I like that. I like the idea of like being in the skunk works dishwasher division when things go wrong. I imagine like that scene of Willy Wonka where like the bubbles are just shooting out everywhere of that.
That's pretty much what it was. Yep.
Okay, great. That satisfies me.
Minus the candy, I guess. But so that was kind of my introduction to corporate America, and I decided I wanted to get away from that. And right. But ended up going down to, looking into grad schools, wanted to go to a bigger school. So as you know, obviously, and some listeners may know, Case Western, while a good school certainly is in Cleveland and is in sort of the Northeast, which is where, or the Great Lakes, probably better way to put it, which is obviously where we're from. Yep. So I wanted to get away from that, at least just for life experience purposes. So explored the Southeast and just sort of looking at colleges around there and got hooked up down in Texas at UT Austin, which, hook 'em indeed. And you can't really call that the Southeast. Anybody who knows anything about Texas would barbecue you pretty quickly if you tried to do that. But got down to Texas. Spent a little bit longer than I wanted to down there, but had a good time. Austin, as you know, is a great place to spend a little more time than you were anticipating.
Right.
There are worse places to
keep you occupied outside of school, right?
Indeed.
And you were still doing bio stuff. I remember something about like the force of acceleration on cells or something like that.
Yeah. So that was one aspect of it. And actually, to tie it back to the experiences I had in undergrad and mentioning the sort of cartilage mechanics. So that's kind of at the cellular level where you're looking at the impact or the role of mechanical forces in driving cartilage maturation. So that's really, that's an interesting level on its own. But what we ended up doing, or what I did for my dissertation work, was related to molecular dynamics, where we were performing, supercomputing simulations on the atomic level for individual proteins and looking really at the role of mechanical load in unfolding those proteins, which is kind of an inverse problem to what a lot of people talk about with respect to protein structures and things, where really, the holy grail is to be able to take a DNA sequence and turn it into a three-dimensional protein structure. And while that's getting closer, we were going the other direction, and we were really looking at, for disease states, how you might be able to, or how the body and how biology might have designed certain disease states to kick off based on load application, where you might get a partial unfolding of a protein that exposes a binding site for some other molecule that then leads to a cascade of chemical effects that then, causes disease or something like that. So it was all very interesting, and obviously we were looking at some really sophisticated modeling approaches and things. But as that description probably invokes, it was a little bit pie in the sky and a little bit far away from actual applications.
Right. I would think that like by the time that a protein starts unfolding, it's in pretty bad shape. Just otherwise.
Yep. There's definitely something going wrong. In some cases, your proteins are going to unfold during normal use. But really, if you think about what application that might have, that could potentially have drug delivery or drug design applications down the road. But it was so far down the road that, it was tough for me to really see where that would actually be used and kind of got. I found myself farther and farther away from, actual hands-on application type engineering. Certainly. Right.
So I'm curious about that too, because, I was actually thinking through, like, we haven't had too many people get to the PhD level on this show. We've had Dr. Howard Johnson on the show. We've had Dr. Rick Sharvat on the show, Dr. Dimitri Netaspazov on the show. So we've had some, but actually, I guess Bunny Huang as well, Dr. Bunny Huang. But most of the time, we are very focused here on, more the more hands-on, the more application side of things. So I am interested in that. Before I do that, I want to make sure that we still have people held here, because we're getting there. And the crazy thing about all this stuff, and the thing that I was actually surprised about when me and Cruz, I call Steve Cruz sometimes, when we reconnected, was that Steve is actually in the same industry. He's in electronics. So we are getting there. Yeah. But let's keep going down this path.
Yeah, exactly.
Just keep people hooked in. Hopefully they're still there.
Hopefully you are still there. Because I do think it gets pretty interesting. And really, the off-ramp from grad school into industry came from, when you're in a PhD program, you're often exposed to funding sources and the difficulty getting funding. And that's really where things went off the rail for me, because, I didn't want to be in a situation where, obviously any occupation you get into is, subject to capitalism and so forth. But but what I didn't like about grad school type stuff was, now you're subject to funding levels dictated by Congress, and that can change, by term and all that sort of stuff. But so, certainly not to get into politics, but, I didn't want to be, sort of beholden to those sorts of funding mechanisms. And really, I wanted to focus more and try to get back to more application level work. And so yeah, and it's interesting.
What is the split you'd say? I mean, you've probably, you had cohorts when you were in a PhD program. Yeah. Did you see people also do the same thing of that off ramp that you mentioned? I mean, moving into industry or moving into getting paid, hopefully. That's I always wonder too. It's like, yeah, you're in school a long time. How about money? You guys like money?
Well, right. And that's another, obviously really important aspect is, when you start looking at some of the salaries, and obviously if you're in a really good position at a really well-known school and you're bringing in a lot of research money and so forth, you're probably doing pretty well. But as you see in the news stories every once in a while, and probably more frequently than we'd like to see, it's very difficult to get tenured positions. It's getting more difficult. Sure, yeah. So, of the cohort of folks that I was in school with at UT in mechanical engineering, I'd say a good number of them, and I'm not sure on percentages, but it wouldn't shock me if it was 50% or so, went into something that was more application driven and more industry driven, where, they probably very much like me probably got in with sort of high ideals in terms of, I want to be a professor. I want to live that life that, maybe you see on TV of just sort of,
I want the elbow patches.
Exactly. The elbow patches. Totally. And to this day, I don't have elbow patches, but, yeah, there's always time, I guess, but maybe an adjunct position or something.
Right. But you get extra patchy for adjunct because they pay even less for that.
That's right. Your patches are tiny.
They're everywhere. You need more patches because your closing is falling apart.
You got to make up. Right. Yeah, so I would say a significant number ended up going into industry when they really started to look into the economics of what it looks like to slog through a postdoc, maybe multiple postdocs, get an associate position or an adjunct position or something, and really have to live your life off of that. So, in terms of my motivations and how I got into electronics and really kind of working in that field, a lot of it was enjoying the research that I did, but recognizing the lack of applicability in the short or medium term of that research to anything that, would matter for things that I see on a regular basis. And then also, just looking at the pure, the idea of, what would be comfortable, what would be something that, I wouldn't have to be scraping by, sure, in that role. And that's not to take anything away from the people who choose to do that. Obviously, that's a great role for a lot of people, but it just wasn't something that I was looking to do. So when I was looking to...
So you were just kind of like looking more towards industry, you're saying, in general. So you were like, okay, well, where are the jobs? Go towards that and see what kind of pops out.
Yeah. And what would, because I did a lot of simulation work, there is a good bit of, and really I'd say that the primary industry where molecular dynamics and sort of atomic simulations show up, at least that I saw at the time, was in drug discovery and sort of the pharma approach and realm. And so I initially contacted a bunch of companies out in, this Boston area, as well as other places where you have hotbeds of biotech and pharma and so forth. My research was even, a little bit too far afield for those folks. But interestingly, the company that I work for and ended up getting a job for, Exponent, that we are the type of place that sort of collects people with unique backgrounds and people who work in interdisciplinary research fields. And so, the stuff I was doing, the protein unfolding, the protein simulations, that's not anything that we're working on. And, obviously is being on this program, we're talking about electronics, but, it's the sort of place where if you have good fundamentals and you understand your field and you understand and have the ability to sort of contextualize fundamental mechanics in different areas, you can make a good progress and start your career in that area. So I ended up getting hooked up with some folks at Exponent, talked to a bunch of different people, first in, sort of a polymers realm. And so proteins are basically just polymers, but ultimately got directed into a mechanical engineering position out in our Menlo Park office, which is our headquarters, where I ended up doing or starting in on doing a lot of computational work where, on that scale, instead of looking at atomic motions, now you're starting to look at continuum mechanics where you're into finite element analyses, things like computational fluid dynamics and things of that nature on a much larger scale, and this is where really, led me to realize that I had made a move that I was happy with and satisfied my goals in terms of leaving academia was, one of the very first projects I worked on was something related to a consumer electronics device that I'm not really at liberty to discuss exactly what it was, but it was something that, I saw on a regular basis. And so we were working on this project for this company. And so like the very first day I walk in, I'm like, bam, there's something that I'm working on. It's a problem for people. It's a problem for this company. They're trying to solve this problem. And I'm helping in a not insignificant way to solve that problem for them, to help people, help consumers, help the company, all these sorts of, really hands-on, really applicable outcomes of my work.
That's great. Yeah, that sounds like it sounds like whereas most, PhD research to me, it seems like the way I've heard it described to me is you keep finding, the shallower or the narrower and narrower field, and you become an expert in that. So you're just diving down into this this hole, not a hole, but like a tiny drill into into the crust of the research earth, right?
Yes.
That is what you're trying to do. You're trying to get as deep as possible.
Yeah.
And it sounds like the thing that you've been able to do, and this kind of like this consulting level in the PhD with the PhD, but kind of at that higher level is now like kind of backing out and being like, oh, well, how does all this stuff tie together, and kind of zooming out from the cloud level.
Exactly.
But then also being able to drill down in these small areas and figure out where you need to drill almost.
Yeah. And so, one of the models for thinking about what a PhD really is that it's a demonstration that you're able to, suffer a little bit, certainly, but also you're able to sort of see a project through. You're able to, ideally, you do advance the field. In theory, you don't get the degree until you've done something that's novel. But, really the big focus is on understanding the fundamentals of how your research relates back to some of the more well-known aspects of whatever your field is, and where we really try to capitalize on the experience of our consultants is in encouraging them to take their fundamental knowledge, the sort of stuff that you would get in your graduate level classes, even your undergraduate level classes, in your boards or your sort of oral exams that you take prior to qualification for the getting your degree, and really use that level knowledge in support of solving problems for people and companies and things.
That's good. Yeah. So let's get into the Exponent level then. Yeah. So you'd mentioned consumer electronics. Obviously, that's the side of things we're going to kind of play in. We're going to obviously talk about electronics, how this stuff relates to electronics, and the mechanical side of things. But who would actually end up calling Exponent, right? So like, what is the size of company, the type of company, the type of product that would end up calling? We like you already said, you're not gonna be able to talk about details, but we'll talk about, generic company types and and product types and situations. Totally.
And really, the answer to this question, I think, is one of the things that most satisfies me about the position, because there isn't really an answer. It's kind of all companies, which is really exciting. Really? Yeah. Because we, as I mentioned, we were working that first project that I alluded to was for a company that makes a laptop. So, if they're making a laptop or that scale of a device, they're probably going to be a pretty large company, right?
That's kind of what I was getting at too. Is like, what is the scale of company almost like? So we see. Are there small businesses too though? Like, and mostly wondering because if people are listening, are they going to be able to, like, so say they run into a problem, are they going to be like, they call you guys up and you're like, well, it's a $250,000 retainer type. I don't know anything about the money, but like just accessibility too.
Totally. Yeah. So we do run the gamut. I mean, those companies are the larger end of things, obviously, but we work with a lot of startups where, and I think actually our model can plug in really well with startups in a lot of ways, because we have, in some sense, we have a surge capacity to overcome problems. So you can imagine a startup, you've got the founders, you've got the sort of initial employees, you've got sort of the core of your team has, certainly, or presumably really strong capability in whatever their area is. But they often, need to branch out beyond that. There's aspects of a product design that they might not be super familiar with, but they need help with it in order to really accomplish what their primary objectives are. So we can sort of plug in those circumstances where, maybe you're a bunch of electronics folks, but you need a mechanical engineer to help you with your design aspects, or maybe you need somebody who has materials expertise to understand something about whether you should make your enclosure for your device out of V0 plastic or some other type of plastic, or all those sorts of things. So we do run the gamut of these really large companies where we're plugging in on very specific levels on a project or a program level within those companies, all the way down to startups where they've got a problem that they just don't have the internal capabilities or expertise to handle.
Okay, so like, what is how well defined of a problem though too? Because you say that we plug in a lot of these places, and I do believe that, but I also wonder about, like, is it like, oh, I need a board made, can I call Exponent? Or is it more like I'm making 5,000 boards a year, and I have a specific heat problem in this one spot and I can't figure it out, and I need to deal with that.
It's definitely the latter. So one of the things that we make sure to be clear about with companies is that there's a positive aspect to this, but we don't do any design work, so we don't stamp any drawings or anything like that. But what that ultimately does is it gives us a plug-in with startups and companies that are concerned about their intellectual property, because we don't retain any of that. It's it's all yours. We work on behalf of you, right. But really it's more on the level of sort of the classic place where we interface, is that some company has an issue, they've got a problem, they don't have the internal capabilities or the time, which is a capability in some sense. They don't have the capabilities to deal with that problem. And so, maybe it's a thermal issue with respect to their board. What are the consequences of that? We've seen a lot of different types of projects, so we can come at it from, ideally having that level of expertise to answer the question and handle the question, but also having that experience level of working in this field, seeing a lot of different problems, and ideally being able to diagnose the problem, hopefully quickly, to get you your answer.
Yeah, that makes sense. Yeah, because I would imagine, like, if I make a board, and so let's just go through a quick design exercise, I suppose. So I make a board, it's got a microcontroller on it, it's got a battery, whatever, and the product starts on fire at some point, right? Mm-hmm. And it happens after, it's being shipped to the customer, and the customer opens it, and the first time they turn it on, it starts on fire. Yeah. Like, that is a very specific problem that I might be like, I don't know. Like, I could probably go through and try and replicate things, but at a certain point I might be like, well, I'm guessing there's some kind of failure here. Mm-hmm. Then that's kind of the call situation, or what? Yeah.
It's, we get called when there are problems, when things are on fire, kind of the oh snap type moments, where a company doesn't necessarily know what's happening. They need the help, and they're under some sort of time pressure. So, another sort of classic example would be if a company, is facing a recall scenario where, they've developed something, they've got an issue, they've got a product out there, and they need to decide whether the problem is widespread enough to justify a recall. The CPSC, so the government's kind of breathing down their neck maybe and trying to figure out, or demanding answers as to why this is happening. And
maybe they're telling people not to take stuff on planes. They're like saying, you're going to get,
yeah. And that's actually an example of a project that we can talk about, because we did work.
Really?
Yeah. Well, so we were one of the, we do quite a bit of battery work, particularly in this office here. And one of the things that we've done, that we are able to have publicly disclosed is our work on behalf of Samsung in dealing with their battery issues there.
Oh my!
Yeah, and so that was a scenario where they were looking to make sure that their consumers or their customers were safe, basically, right? They had these issues. And they came to us because we have, in that field, in that sort of battery realm, we've got a lot of experts who have really well-known expertise, I guess. And so we got involved in that. It was a quick, pardon the phrase, but a quick burn type scenario where we needed to get answers on behalf of Samsung in order to guide them and provide sort of advice in terms of how to approach that, and really, where can we identify what the problem is, and that was the initial goal of the project, was just what's the problem, and then once we figure out what the problem is, then concert with all the stakeholders, decisions can be made about how to mitigate that problem.
Sure. Right. And I'm guessing the consulting fees compared to that was probably to the actual recall was a drop in the bucket.
Oh yeah.
But I mean, given what they did, I mean, like, obviously they caught a lot of flack for it, but like they did probably the best they could from what what ultimately was a design flaw.
Right.
But nobody died, so that's good.
Yeah, that's definitely an important metric. But they did see quite a bit of company value erased as a result of that. At least initially, right. and nobody likes to see that happen. But they survived it. Obviously, they've got a lot of good products, and they're
and a lot of money. That helps too.
That does help too. Yeah. For a circumstance like that.
What was the problem? I'm trying to remember. Was it like it was a mechanical spacing issue or something with like the closure?
So there actually ended up being a pair of and actually I guess I'll have to defer on that question because I'm not sure. While we did work on it, I'm not sure. I'd have to review a little bit.
You were saying you didn't work on it, but that's fine.
I did actually work. I personally worked on it, which was a cool experience. But what exactly we publicly disclosed in terms of the causes, I should probably hold.
So here I can state what I remember. I remember there being like a gap between but like there was a machined out gap or something like that, and I thought it was like when there was certain amounts of pressure based on the battery pack, there wasn't just quite enough room. That's what I remember.
Yeah, it was a spacing issue, and it related to the packaging of the batteries and how they were constructed. Yeah.
Okay. Well, so then let's talk a little bit about like stepping back a step from that. Obviously, that was an unfortunate situation that did not work out well for the the bank account of Samsung. But is that something that should have been checked before? Like, I don't even know how you would have caught that. You know what I mean? Like, right. Other than like just on a scale side of things, like would a consumer company like that, or just generally a company like that, are there certain audits that they should be doing or simulations like you were talking about that they should be doing that could have caught that?
Well, sure. Yeah, definitely. And, what we see a lot is, and what we are able to help our clients with often as well, is just sort of reliability audits and things of that nature where, you're going in, in some cases for us, it manifests as factory visits and factory audits where, we're actually walking around the factories and checking for anything out of the ordinary, that sort of thing. So there's that level to it. There's certainly a ton of simulation. One of the things I didn't really appreciate before I got into the field, and really before I got a few years deep into it, is just the amount of simulation that's done on anything and everything. I mean, everything from kind of getting outside of electronics, everything from potato chips to potato chip bags,
really?
Everything. Yeah, because they're looking at...
Steve, are you hungry right now?
I am a little bit hungry.
You said everything, and then you said potato chips twice in a row. So
I do like a good potato chip, but there's a lot of stuff that gets simulated. And so, going back to electronics, all of these companies, anybody who's large enough to be putting millions of products out is going to do a ton of analysis. But really, you're looking at extremely low failure rates. And so catching that it almost, becomes more of a statistical exercise than anything else. So we certainly, and as a standard in the field, there's accelerated aging tests that you can do where, and not necessarily even just aging, but it just accelerated testing where you might be trying to replicate what a device is going to experience if it's, exists in Phoenix and is left on the hood of a car on a regular basis. So you might put it in an oven and you might cycle it at some high temperatures just to sort of accelerate the process and try to determine whether or not you're going to get some sort of lifetime degradation as a result of that process. And so you may not actually ever get to the point where in your testing you're experiencing a failure, but what you might see is enough of a degradation in performance if you're looking at some like subcritical metrics. So something that's not actually going to cause, for instance, a battery fire, but something that's indicative of a potential fire down the road or a thermal event down the road. So you accelerate that testing. But yeah, it's extremely difficult difficult. And these companies do a really, really good job of it, generally speaking. I mean, we do hear about the extreme events, obviously, but there's a lot of work that goes into making sure that you don't hear, that there aren't more events to hear about, I should say.
Sure. Yeah, exactly. That is the idea, is that like if that testing wasn't being done, we'd hear about it every other week.
All the time. Yeah, all the time. Because, I mean, you think about just a standard battery, the amount of energy that's in there, but the fact that things are engineered well enough to withstand some of the damage that we expose them to, both, in the field as consumers, but also in our testing as a mechanical engineer. I do terrible things to batteries and have difficult time getting them to do anything fun.
Magical fire bags right there. Yeah,
yeah, exactly.
Yeah, that's tough. So what should be, okay, so now back to the listening audience, what should they be considering when they are putting a battery into a product? Then I guess that's kind of part of the consideration here is, yes, a lot of products have batteries. Lithium ion's cheaper than ever. There obviously is some risks in there, but what should they be doing as general guidelines? And then should they be doing it, or what is this simulation that happens at the end?
Yeah. Great question. So there are a lot of decisions related to, and some of your listeners, certainly know this better than I do in terms of the specifics, but battery management units, the electronics that you're actually connecting to the battery are really, really critical with respect to shutoffs and various conditions on overcharging and trying to avoid those circumstances.
Got it. Yep.
So certainly the software aspect of that is a critical component. From my perspective, when I start thinking about the mechanics of it, there's really two aspects of it, and it relates to a thermal event of the battery that you really want to, as you consider the role, the interplay between the cell or battery and the environment. What you really want to do is you want to protect the cell from the environment. So by that we mean, you want to make sure that whatever enclosure it's in is, for whatever the application is stiff enough or protects the battery in enough ways to really prevent the sort of mechanical damage that could lead to a thermal event.
When you say cell, sorry, do you mean the overall, like an actual 2,000 milliamp hour battery pack, or do you mean a subsection of that?
It was a subsection. So okay. I would refer to a battery as the assembled components, which may include multiple cells and would include also a management unit of some kind and the connections between those individual cells. So some of the cooler things along these lines is, like, if you go and you open up some of the articles on Tesla battery packs, they have just sort of public stuff. They have a number of teardown pictures where you're looking at these little 18650s or close to 18650 cells, which is just describing a form factor of a lithium ion cell. And they're all aligned in rows and, connected in various ways. And so each of those little units is going to be a cell, and then connected together is going to form the battery pack as a whole. So
I was thinking about more like the pouch, like the square pouch style.
Yeah.
If it was like internal to that, if that was a single cell.
Or yeah.
If you meant at the 18650 level, I guess I understand that one.
Yeah, and either way, really, I mean, you could have a pouch cell where you have a soft polymer pouch around the electrodes. You could have a prismatic cell where you have a harder enclosure for the cell for the electrodes. Or you could have a 18650 where it's or similar, where it's a cylindrical design, or button cells. A lot of different form factors.
Okay. So really just anode, cathode, electrolyte is a cell, right?
Yeah.
That's kind of what the definition here.
That's one way to think about it. And you really want to understand from a design perspective, you can imagine if you're somebody designing a cell phone, for instance, your requirements or your design goals for protecting that cell are going to be very different from somebody who's designing a drone where, a cell phone might be dropped, but it's probably in a stiff enclosure. Whereas a drone, if it's flying over a residential unit taking pictures of fireworks or something, and suddenly it loses control and falls down, you may have a pouch in that drone, and it's subject to crashing from 40 feet or something. So you want to know what sort of potential mechanical, from my perspective at least, the potential mechanical conditions that your cell is going to be exposed to, not only during intended use, but more importantly during unintended use. If somebody takes a nail gun and shoots it at your drone, what's going to happen?
Wow, this is like part of your work is like you have to be like, well, what about nail guns? What about hawks?
Maybe not hawks, but we did have a project where I was fortunate enough to rig up a pneumatic nail gun to shoot into a battery and see what happens. And
that's awesome,
dude.
How are you not doing this on YouTube as like as a promotional thing for the company?
we have talked about doing some of those things, certainly.
Yeah, right.
It's finding the time to do it, I guess, but.
Yeah, I guess so. Okay, so you had said the first thing you have to consider is protecting itself and the environment. What was the second thing you had said?
The second thing, and this is something that's definitely overlooked, is protecting the environment from the cell. There's the concept of you don't want the cell to go off. But as with, and this touches back on something we talked about a few minutes ago, these things are statistically driven. They're very low probability events. But no matter how good your process is, you can never engineer out all of the potential failures. So you have to assume that something's going to go wrong. And when that something goes wrong, you want to make sure that your device and your enclosure is sufficient to contain that event, such that somebody's not going to be shot with molten aluminum or something.
Right. So that's the idea of like, and I guess that's kind of also UL testing as well. It's like when failure happens, does it fail properly? Right.
Exactly. And you really want to, again, and this gets back to there's sort of UL style tests where you have some sort of standardized way to test these things. And then there's considering the application and what is that cell and that device really going to experience when some teenage kid gets a hold of it and wants to drive his truck over it or something. What's really going to happen there.
Okay, well, so that's as good an example as any, right? So let's say that the truck driving over device is part of the expected failure mechanism. Is that something that you would then go and actually simulate, or like how do you actually, aside from actually just physically testing it, do you simulate that piece, or what happens then?
We do to a certain extent. So, there are various approaches for simulating the thermal runaway events of batteries. That gets into a lot of different kinetics where you have a lot of chemical reactions occurring and some very detailed analyses that can be done. But I think where you get the most benefit is just from looking at from my perspective is considering the mechanics of it and really looking at taking your device as a whole, where you're simulating the stresses and strains and deformations and so forth of your entire device under this truck loading, and really looking to see, does the battery experience a certain type of stress in a certain location. So one of the areas that might be sensitive for a battery is where the windings are exposed at the top, right? So you want to evaluate, okay, if I drive a F350 over this thing, is the top going to get smushed, or is the enclosure strong enough to protect and minimize any deformation there? And when you do that sort of thing, those are much more established approaches than getting into the kinetics of the actual chemical reaction occurring inside.
Right, because you already know some. I mean, I'm guessing there's probably a bunch of literature around that, like the chemical stuff. It's like, okay, when it hits this certain point, bad things are going to happen. Yeah. Just assume it's going to get worse and worse, right?
Right.
But it's about how do we prevent that getting to that bad point in the first place.
Exactly. And you can get a lot of information just from doing modeling where, really even as simple as considering a battery as just a brick, like with some homogeneous properties, and just put it in there. But you're ultimately want to evaluate the impinging forces and stresses on the cell itself.
Right. So the output of that would be like, you would end up seeing like a vector basically that's kind of going into that brick. Then you'd be like, well,
that's one way. Yep.
If the truck drove over it in this way, you'd see forces here and here and here.
Yeah. And you see hotspots of stresses. And so one of the things we love to make are these color maps of stresses, and they make beautiful pictures. And sometimes they tell you good information with respect to, what type of stress and locations of peak stresses and things of that nature.
So what are the programs what are the types of programs that you use to do that?
Yeah. the program of choice that we use, at least, is Abacus. It's one of the premier finite element software packages, just commercial packages. And so we rely on that because it's already, from a software level, at least, it's been validated and so forth. So, we don't have to worry about software level validation there. But there are a number of
it's made by Dassault too. So
Yeah.
is that part of ties right into SolidWorks?
It does tie into SolidWorks. Absolutely. Yeah. So there's a lot of nice applications that way. There's certainly ANSYS is another option. COMSOL is one that could potentially play in, although its strength is really in some other areas. But, finite element, the nice thing about finite element analyses relative to, going back to what I was talking about with my graduate work was, finite element analysis has been around for 30, 40 years. It's a really well-known approach. So it's trusted. It's used certainly in any sort of major engineering project is going to involve some level of finite element analysis. So we can leverage the trust that the engineering community from a solid mechanics perspective has in those software tools to really get some good results.
So what is finite element analysis for us? For us electro weenies out here, what is? I know this is a big thing in mechanical world, but I'm looking at the Wikipedia page what the heck? Your Stokes differential equations. I remember those.
Yeah, there's some math involved, but probably the best way to think about it is, and most likely people have seen things like this where you have a volume. Let's just even think about a brick. Like if you think about the analogy we were talking about where you take a battery and just assume it's a homogeneous brick, you divide that up into a number of different volumes. So, and we call those elements where you essentially solve those differential equations on an element by element basis. And you're tracking the deformations of the nodal coordinates that form the boundaries of that element. So you're really just looking for the movement of the elements where that movement is governed by material properties like stiffnesses and various things like that you plug in. And it essentially just is a matrix solution type approach for getting you those deformations.
So it's like spice for stuff.
Yeah.
I mean, I please don't write in. I know that it's not spice for stuff. I'm just saying it's math being applied in a generic way to. Yeah. Okay.
Yep.
It is a reverse solver for that kind of thing. Okay. So is it like so if you're assuming a battery is a brick, is it? Like you have a book of numbers that's like, well, battery's a 4,
Sometimes
actual brick's a 7. Yeah, right.
So that gets into a lot of the testing aspects of things as well. So you have so for some generic things like aluminum, for instance, if you're thinking about an aluminum device, most of those material properties are very well known, at least for your basic like stiffness and other sort of generic material properties, strength, etc. For something like a battery, that's where we often get involved, where we want to measure the stiffness of the battery so that we can then use that information in simulation. So it's sort of a two-pronged thing where we'll go and do some mechanical tests on the batteries, not to kill them, but just to understand how stiff they are, and then take that information.
Right. So like, does it flex? A certain amount of force, and you're measuring basically how much it flexes at a certain point, and then you back calculate that into your model.
Totally.
That kind of thing.
Yep. Okay. Exactly.
Does that always go okay?
No.
I guess are they stable enough that it doesn't matter that much, or what? How does that go?
Actually, I think you'd probably be surprised at how stable they are. They're very, at least for most of the manufacturers that we work with, they're very well engineered products, in the sense that you can do some significant deformation to a battery and get away with it. And now it really does depend on exactly how you're doing that. So for instance, there's the concept of just bending it. But the radius of curvature of that bend is potentially going to drive how explosive or not that event is. It depends on how you do it, but it can get really interesting. And so a lot of those tests we'll do in one of our facilities. We have it's actually a restaurant hood, but it's this big air handling unit, and we do all the tests under that hood. within cinder block enclosures. So if anything exciting
nice.
happens, it's contained, it's safe, all that sort of thing.
Sure.
So
that's good lab procedure stuff, right?
Yeah, don't want to kill myself.
Right. And is so like you as the engineer on a project, are you actually doing that? Is it like each test is different enough that you need to basically go and like run experiments on this stuff?
Yeah, and Exponent's model as a whole really is that we shouldn't be doing anything that's standardized. We try to advise our clients anything that's standardized. Go and do it at Intertech or some of the other labs that are set up to do high throughput tests in that manner. But for things that we get involved in, typically there's something unique about it, or maybe multiple things that are unique that justify our role in setting up that test. And so going back to this notion of sort of collecting people who have done interdisciplinary things and have gone through a PhD program where they've done research, everybody who we bring in ideally has the experimental chops to reliably run a test and know where
scientific method, design of experiments,
all that
kind of thing.
Yeah, exactly. Exactly. So
that's important.
Yeah.
So how do you go and back calculate that stuff to, okay, so again, we're talking about a battery as a brick, right?
Mm-hmm.
And now, okay, you go through your finite element analysis, that there's going to be 100 newtons of force at point XYZ, whatever.
Mm-hmm.
But then you Steve, the PhD smarty pants. Sorry, that sounded way negative, more negative than it should have been. You, the consulting engineer.
There we go.
You at some point someone has to say, oh, this is bad, right? So how do you know? Like, so I hear 100 newtons of force. I don't know that I made that up, but at some point you have to say that is going to be problematic. So how do you calculate when that's going to be a bad event?
Yeah, so that's sort of the third level of analysis, where you've done your first sort of material property testing, where you just want to understand what's the stiffness of the brick. Then you go and you do your truck simulation. You drive a truck over it, and you say, okay, you're getting that 100 newtons. Then you say, okay, well, if I'm getting 100 newtons in that location, is that something I need to worry about?
Right.
So you set up another test where you apply that load in that location under the conditions where you're trying to match what you are seeing in the simulation in terms of the worst case scenario. And you're trying to recreate that worst case scenario in a lab setting to understand whether or not that's going to cause something that you should be concerned with.
Oh, okay. So I was actually thinking it was going to be like another... you'll have to excuse me here. I thought there was going to be like a book that's like, well, if there's 100 newtons of force, batteries explode. But obviously, like that, I know that doesn't actually exist. But I just mean that at some point, I thought there would be like a calculation that's like, don't have too much.
Yeah.
Like if the liquid expands too much at this point, it's going to cause a heat. Something.
Yep. Yeah. So there are certain sort of rules of thumb that you'd want to avoid, but that's much more well established for something like a generic metal. So you can think of, there's this website called MatWeb that's just got these lists of all these different materials, and it has their, mechanical properties is one of the things that's included there. And one of those mechanical properties, or maybe a few of them, are the strength of the material. So for your generic aluminum, at what stress is it going to break? So that's very well known for something that's homogeneous and established like an aluminum. But when you get into something like a battery, for instance, or solder, or anything that's maybe got less well-established material properties, particularly with a battery where you have chemical kinetics and you have other things going on, it's very difficult to a priori say 100 newtons is going to cause this stress, and this stress is the failure point. You really should be doing some sort of testing, because your chemistries are going to be different, potentially for different manufacturers, even with the same specifications. Your chemistries could be different. Your kinetics could be different. A lot of different things could happen that you need to test out.
Got it. Okay. And so that's why at that point you're saying that you're saying here's a worst case scenario, because that's going to be the worst thing. We're going to try and replicate this 100 newtons of force. And again, we're making up all these numbers here. Yeah. People are like, 100 newtons. But if you're going to be able to then apply it repeatedly in some controlled environment, and then you're going to have a statistical model. Like you might age that battery again to see if there's a negative impact of that kind of thing, and throw whatever you can at that point. Is that kind of the idea?
Basically, yep. And those sorts of things, because of how involved it can sound, you really only want to do on some of your more significant events like a truck. But ultimately, it's something where, as a designer, you need to make an evaluation of what is my device going to experience, and maybe some of that you get from product knowledge, where it's been out in the field and you've gotten some returns, and those returns have tire tracks on them. Something, or it's got a nail through it.
Right.
And we laugh about some of these things, but we also do a lot of sort of failure analysis on things that have gone wrong, and we see some crazy stuff. So,
well, I mean, that's the thing, like, especially with consumer stuff. Like, I've never worked in the consumer space, but I can only imagine, like, just the sheer number of like events that they have, let alone the really crazy ones, you know, like
totally.
And then some of the people that try and return them for refunds too, I'm sure is like, oh, what happened? Right. No, we don't cover that one.
Exactly. What do you mean? There's a 16 gauge nail sticking through this thing. No, we're not covering this.
Right. Yeah, that one didn't make the cut. No. Sorry. Okay. So what pops out of all this then? So is it like, again, I know we were making like a crazy scenario here, but is it like, you have a report that's like, well, in the truck driving report, or what?
Yeah, basically. So,
I mean, how does it get fed back into the next design cycle for the companies that you might be working for?
Sure. Yeah. So, in that scenario, we would let them know what the results of the tests are. And typically where that plugs in for them is that they might say, okay, well, under this worst case test, we see that we need to enhance the stiffness of the enclosure in this location. And so they'll have their, CAD guys go in and modify what the enclosure looks like. Maybe they'll add a new component to provide some additional stiffness, or, whatever the case may be.
Right.
Ideally, they're going to take that information and they're going to understand their vulnerabilities, and then they're going to modify their product to overcome those vulnerabilities.
Well, I'm guessing that in the case that Exponent's being hired as well to do something, it's probably it sounds like a lot of this stuff is reactive versus proactive, because in a proactive scenario, it's like there's thousands of millions, unlimited number of things that could happen to a product. How would you choose it? You'd have to have as many, it'd be like monkeys and typewriters type thing, right? Except the monkeys are not typing, they're shooting nails into things.
Those are crazy monkeys. You see any of those, you run away. But
right, exactly. Well, that's right. Yeah, never trust a monkey with a nail gun.
Nope. And you bring up an interesting distinction there between reactive and proactive. So, we classically work on, the company was founded as sort of a reactive firm that, back in the day was doing things like airplane crashes and bridge collapses and stuff like that.
Sure. Yeah. Right. Back calculating what happened in the first place, right? Like what actually, what went wrong? How do we not do this ever again?
Exactly. And we talked about the Samsung example. That's a scenario where that was, what we would call reactive, because something happened and, we want to understand what happened there. But we do see a lot and many, in fact, most of the things we can't talk about are things that are proactive, where, we're involved in the design cycle. And while we don't design anything, we're advising on design choices. So should you include that structural rib in that location, or should you move it? Things like that. And really the motivation for that, often what I see at least, is that it comes out of companies' internal reliability testing, where, again, the amount of testing that these folks do is really impressive, and gives me at least a lot of confidence in products. But they will identify some issue where it's some stapler and they're dropping it in 10 different orientations, and it always breaks or ejects a staple when it's dropped in the 7th orientation. And so, there it's a question of, okay, well, why is the 7th one worse than the 6th or the 8th one?
That makes sense. Okay. And that is good too, because it sounds like that's the time to call, not that they wouldn't call you sooner, but I'm just saying that at that point, if you are doing these, ad hoc, real life situations, at a certain point, you could dive into it yourself. You might have someone internally at a company, but that's also something where you might call a consultancy like Exponent to do that kind of thing.
Right, right. And typically in those scenarios, there's something, by the time we get the call, they've tried to fix it, and, they are running into some sort of roadblock. So,
Sure.
maybe it's something that requires a different discipline, knowledge of glass mechanics or whatever.
Right.
So they may call us, or it may just be that they don't have the bandwidth. So, everybody's tied up on something. Yeah.
Yep. That makes sense. Cool. Well, before, we're starting to run out of time. Amazingly, we've talked about enough nail guns, I suppose. But but I did want to talk about the other piece you had mentioned. So you had mentioned CFD, which is computational fluid dynamics, if I remember my intro classes. What is that stuff? Because you had mentioned BGAs as well. Again, specifically to the electronics industry.
Yeah, and we got off into the battery tangents, which is something that's really interesting, obviously. But the BGA side of things and looking at solder performance and things is a strong component as well of a lot of the electronics work that we do, at least, where now you're looking at, on a board level, you're trying to understand failures of products, and in these circumstances, more often than not, what we've seen is that a company has put these into, maybe it's a thermal cycle, where they're just baking these boards as just part of their normal reliability testing, and they start to see some sort of failure.
Well, like the same thing of like Arrhenius equation, trying to do like trying to do accelerated life testing, that kind of idea.
Yeah, exactly. And so, some of it may be motivated by returns, but, more often than not, they catch it before that it gets to that point, and they've seen some sort of reliability issue, and then they want to understand, okay, well, why is my solder ball in this one position failing? What's really driving that? And so that's where we get into these ideas of heat transfer, where CFD is, going to be a prime tool to evaluate that, as well as finite element analysis for sort of other applications. But the concept of your heat transfer paths and really what happens when you have a certain board location heat up, how does that change the stresses in the solder on an adjacent chip, for instance? Those sorts of questions, can really come into play. And I was just listening to, I think it was maybe 6 episodes ago, was your conversation with Dave about the BGAs, and you guys were talking about solder masks and those sorts of things. You're really getting into those questions of layout, and where I come in and think about that is, you have this potentially a massive chip, if you're looking at like a motherboard for a laptop, right? Really can dominate things, and everybody, you have an FR4, which is going to be, it's a composite with some copper layers and things, so it's going to have a stiffness, but you're going to have silicon chips in there, you're going to have overmolds, you're going to have all sorts of stuff going on, and where, from a mechanical engineering perspective, where that gets really interesting is, as things start to heat up, you have different expansion coefficients of those materials. And so, one material wants to expand a lot, another one doesn't want to expand, and the poor solder's in the middle, and it's got to deal with the fact that the board is expanding maybe more than the chip is, and, it's cupping or something or saddling, and what is that really going to do to the stresses in the solder balls?
And are you saying this about the actual assembly process, or you're saying after the board has been assembled and it's just trying to keep the chip connected? Okay.
Yeah, so we've done a number of projects where we've looked at the whole reflow process of putting chips on and what really what those balls are experiencing, and that gets into, so there's this concept of viscoelasticity, where you have some sort of time dependence of your material properties, and you have the ability of stresses to relax out. So you want to, in some cases, you need to incorporate the fact that you've got a chip that you've applied to the board, and then you're putting it through another reflow process to put another chip on, and you're deforming the board, and now you've got a board that's because of the expansion process, because of the cooling process, as you're taking it down from out of reflow, now you're really, you've got a deformed board, you've got solder ball stresses. What does that do over time? Do those relax out, or do those result in cracks through the solder that then can lead to, drop signals of some kind?
Right. Actually, I have dealt with, maybe not specifically this situation, but I have talked to people. I work with a lot of like modules that are actually like chip on modules, like they're pre-certified RF modules.
Mm-hmm.
And they talk about like reflowing those and like the need to bake them out again. So like say you want to remove it off a board and solder it back down, they're like, don't do that. That's a bad idea. And I think it's because, and if you look at it, it's like sandwich on sandwich on sandwich, right? These days, you put down an RF module, that's effectively a tiny, probably not FR4, but some, fiberglass controlled impedance board with an RF chip on it. It's been tested. It's got a metal can around it. And then I'm going to solder that to like an ESP32, right? That's, I guess maybe that's not a good example, but like a little Bluetooth module or one of the ones with a metal can around it. You go and solder that to another board in a totally different way, and now you get stresses that are just stacked up and up and up and up. So
exactly. And then once you start looking at, okay, well, you've got those stresses baked in. Now potentially you're doing this reliability testing where you're putting it in an oven and you're running it through some thermal cycles, or maybe you're taking that board and then you're exposing it to a drop scenario where you take a device, you drop it on the ground. What kind of stresses are the balls going to experience? And as a result of that, it's possible that you end up with, due to the manufacturing process, you end up with something that's close enough to the failure point that all it needs is just a little more stimulus, which it may see during the drop process.
Well, now that we've scared the absolute pants off everyone listening who's made boards, let's talk about some practical, like what people can do for best practices, or maybe when they should call someone like you, right? Because I mean, like for me, like I've done this before, and it, most of the time it works, right? I'm obviously not making millions of anything, so I don't need to worry about it that much. If it doesn't work, I grab the next one. Not saying that's my design method, just that's my practical way to get through certain prototyping issues.
Yeah.
So, somewhere between prototyping and making a million, when do people call you, and why should people call you?
Yeah, it's a great question. So, I think there are a number of good practices. From the perspective of board layout, that's really a question that is not something that I'm in a good position to answer, but certainly with respect to supports and considerations for how you mount your boards, that's something that you really want to think about, what sort of deflections you're expecting your board to experience, where, again, really we're looking at, or I'm considering scenarios where you've exposed your device to some sort of mechanical perturbation, like a drop or an impact or something like that.
So that's like a board mounted inside an enclosure that's going to be hit the ground at some weird angle.
Yeah.
Is that the idea?
Exactly. Yeah. And we do enough of these simulations, and one of the benefits of them is you can see what happens on sort of a microsecond time scale where you're watching the board vibrate. And so, those, it's really interesting. But, that speaks to the importance of supports. It speaks to the importance of, if you have a large chip that may dominate the board, trying to make sure that you've got, your sort of subordinate chips spaced far enough away, if you have the luxury of space, spaced far enough away from that larger chip, because you would expect that larger chip is going to keep things in its vicinity pretty flat, and then you're going to get large deformations coming off of that if the board as a whole wants to move.
I see. Okay.
So it's this notion of just sort of chip spacing. So, but really, when you should be looking for assistance is a scenario where you've designed something that is working fine in isolation. If it's not under some sort of stimulus environment, but you really are expecting it to experience some kind of stimulus, or you're noticing that during its normal use, maybe it's a thermal cycle event that's you weren't expecting it to be all that intense, but you're leaving it in the car, or maybe it's some sort of connected device, or
I see, yeah,
maybe it's a LiDAR, for instance, where you are. Microns could be really important with respect to resolution. So you need to make sure that you understand what sort of thermal deformations you expect to see in your device in order to keep the sensors true to whatever the datum is that they're supposed to be at.
Got it. So if people are doing like tolerance stack ups and they're doing high reliability situations, if they're doing high stress situations, those kind of things are where this really, really comes into play, it seems like.
Exactly.
Also, it sounds like larger chipsets, right? So like, just because the thing that's planar and needs to be flat, expects to be flat, and you're talking about like leaving chips away from that big mama chip in the middle.
Right.
How does this play back into the computational fluid dynamics side of things? I mean, like,
right, yeah. That's a good point. So we talked about this idea of reflow, and in those circumstances, typically it's homogeneous temperature. But the interesting aspects of the CFD, for instance, is when you start running chips pretty hot, so or exposing them to environments where heat transfer is going to be really important. So if you have let's say an outdoor wireless router of some kind, maybe that's going to be exposed to temperature. I always think of automotive too.
Totally. Like automotive, like they're running hot, they've got crazy processing, and then they're like, oh yeah, and this can work up to like 85C, no problem. Yeah. So that means you have temp rise on top of 85C. It's like, holy crap.
Yes.
And that's insane to me.
Yeah. And so the CFD aspect of it, and where the simulation side plugs in, is you want to understand how easily the device or the board or whatever is shedding that heat that's being generated. You need to look at, maybe the die is heating up quite a bit, but it's got heat transfer pathways, down into the board and through the traces in the board, as well as it's convecting up and away based on whatever the airflow patterns might be. So, there are different scenarios and different cases where you might look at a forced convection where you've got wind flow over or airflow over your board, but more likely you're just looking at sort of ambient temperature distributions and sort of non-forced convection, just sort of natural convection away from the board. And there you're calculating, you're ultimately just trying to determine how much heat am I getting away from this chip? And as a result of not being able to get all of it away, what's the resulting temperature of the components?
Right. Well, I can imagine too. Like, so I've had, I remember I used to have a cell phone that was like, anytime you took a video, it got just like roasting hot.
Yeah.
And, like, because image sensors just heat up a lot and they take a lot of power and blah, 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 blah. But then, then tying that back to earlier, where now you have a chip that's generating a bunch of heat, and then it's on the backside of a battery. It's like, oh, okay, well now you have to then go and double check to make sure you're not heating up a battery in a bad way, or doing that kind of thing too. Yeah, you do.
So, and all those things tie together. And you also have the sort of the human factors aspect of it. So you mentioned this idea of it getting hot, but potentially if it's a cell phone, for instance, you might be holding it against your head, and everybody's experienced the scenarios where the phones really heat up.
Right.
It's possible that something like that is gonna, they're engineered to the point where they're not gonna result in any sort of uncomfortable experience, but you do want to consider
lest we forget the Sony laptops that were known for heating up a little bit too much in the lap region.
The lap region, indeed.
There were some bad times had by all in that scenario too.
That's right.
So like that, in that scenario though, like they didn't do that calculation, or they didn't know what was going on, and I think they had a recall on that too.
Right. So that, it's possible that, so obviously your devices are going to have some fan of some kind, and, maybe it was just underpowered or it wasn't working properly. I don't particularly know in that circumstance, but, ultimately you're not shedding the heat. And it may be too that they were expecting it to be elevated off of a surface. So maybe there's feet right. But if it's sitting on your lap, your body's not very good at conducting heat away. So it's just going to absorb it, and it's not going to transmit out.
And so that's part of the human factors, like you're talking about, of like actually seeing it used in situ, understanding what's happening. And it's like, I guess that's like a product testing as much as anything else, right?
Yeah. And, there's user studies, and there's things that, some of the larger companies do to just understand how is this going to be used, and in those circumstances, what is that doing to all the potentially vulnerable components?
I mean, how much of the time are people coming to you because they're like, well, look, we have to operate on the edge of this, like there are specs, and at least for me, like I'm very rarely pushing specs because why would I be? I'm not designing anything crazy anymore, but like sometimes like a car company might be pushing a specification because they have to be, right? They're operating in Dubai in an automobile, whatever. How often would you say customers are coming to you and being like, look, we just have this scenario and it mandates that we're on the edge of the specs, and then we're going to calculate if we can get away with it. Is that not get away with it, but you know what I mean? Like if it'll be sufficient margin to operate.
Right. Yeah, it's not as often, thankfully, it's not as often as you might think. So there's usually pretty good safety factors built into a lot of these things. And I think where they're operating to the edge, there's usually going to be there's going to be some sort of sensor issue where it's really the functionality, not necessarily the anything dangerous that they're operating under, thankfully. But for instance, part of the march of lithium ion batteries in terms of getting higher energy densities and so forth is shrinking some of the layers that are involved in that process, where you're making things thinner in order to pack more into the same volume, and that's a circumstance where really ideally you're doing a lot of testing to verify that any changes you're making in order to pump up your capacity are not limiting other aspects of functionality.
And that might end up, and hopefully that's also being done at the manufacturer level too, so that when they specify it, they're like, well, now we've changed our boundary box because we are going thinner. We're going to give you a thinner battery. That's what you asked for, but don't do A, B, and C now because it's the margin has shrunk for our side, right?
Yeah. Yeah.
So that's lots of
there are a lot of things to think about. Certainly keeps us busy, but but
that's good.
Right. But it's also really, when you start to see the interiors of some of these larger companies, it gets, I do have more of a sense of ease, I guess, because there's a lot of really smart people working on, really important problems in terms of trying to get some of the more, what may seem functionally to be a minor gain in performance. It can be a result of, as you mentioned, pushing things a little bit in terms of thinning things out or whatever the case may be. But tests are being done, and people, really are paying a lot of attention to reliability, because it doesn't take much to show up on the front page of CNN for something that ultimately may not be your fault, but the social media costs of something like that, may be large
public
enough.
relation nightmares.
Yeah, exactly, exactly.
Okay, so what when you do have an issue that's like, so again, to kind of talk about what is the stuff that is output of this analysis, right? So the CFD analysis, what is the output then? Is it like, oh, move this via, or like what is it that you would then tell them to do?
Right. So some of it might be as specific as move a via, or move their chip a little bit in this direction or that direction, or give yourself a little bit more spacing or something along those lines. Other aspects might be something that we see often is stiffeners. So sort of board stiffeners that you might put in to protect components or to keep things planar. Some of it might be some of these underflow or underfills that you might put under a large chip to provide additional support between the board and the chip, so that not all of the mechanical compliance has to come from solder. So it might be a matter of changing up the formulation for that, and using a different underfill, for instance.
So that's good to know. I mean, because I guess ultimately, if you look at what the normal outcome of of recommendations is, I know that it won't be standard, but if you look at the outcome, then that kind of also gives an idea of what some of the issues were in the first place. Right?
Yeah, exactly.
So like you were talking about flexure there, and you're also talking about heat transfer and all those other things.
Yep.
So I could imagine there's unlimited things you could suggest, but it's good to know kind of what has been suggested in the past.
Yeah, and typically, the result of one of these analyses is most often a specific mechanism for why something did what you didn't want it to do. And so those specific mechanisms are typically treatable in some way. Right.
It's a very bounded problem that's difficult to solve, but obviously you are solving them, and it's like, okay, so there's going to be a solution for a bounded problem, which is good, right? I mean, that's science.
Yeah, exactly.
Science. Speaking of science, to take it back to the beginning, so is this something that Exponent and you and your colleagues, is it something that you publish about, or is it because it's being paid for by the companies that it all stays internal?
More the latter. One of the things that's nice about the company is we are encouraged to still stay in the scientific and engineering community with respect to conferences and publishing things. So where we might publish and typically do publish is something that we want to potentially educate the the discipline about. So it might be something that we're seeing in specific projects for a client where it's, a particular component is causing issues across the field. So, there's a lot of different companies facing these issues, or maybe it's something that we see as a potential issue down the road. We may want to alert our clients with respect to, and all of them potentially that, hey, we've seen this issue.
Right.
Let's stay away
and
from
even
it.
like alerting your coworkers in a public, I guess you have to be kind of quasi-public, internally at least, to be like, if you see A, you may also see B, and watch out.
Yeah, so there's some institutional knowledge.
Yeah,
exactly.
Yeah,
but yeah, we do try to publish, and a lot of that relates to just staying current in the field. Also, that's obviously a very important component of what we do, is making sure we know what the latest technologies are and so forth. So some of that relates back to publishing and staying in it. But a lot of the stuff, as you pointed to, is funded by clients, and we take that confidentiality very, very seriously. So we don't often publish things that are specific to clients.
Yeah, right. It'd be like if it was public enough, and if they were willing to publish it as well, that kind of thing.
Yeah.
What are some of the conferences that you would go to for this kind of stuff? Yeah,
so I get involved in a lot of different areas. With respect to the battery work, there's a few larger battery conferences. And I forget some of the names right now, but I often actually do I still work in the medical device field as well. And I go to a number of conferences that are specific for like cardiovascular modeling and things of that nature that are a little outside of what we're talking about here, but also work in some of the additive manufacturing areas where we're going to like polymers conferences and talking about properties related to that. Yeah.
That's cool. Yeah. Okay. All right. Well, if you think of any, we'll add them to the show notes. Definitely. But so y'all hiring? Is that something?
Yeah. We always are. So we do have a pretty, I'm not sure I'd say strict, but we do try to look for folks who have their PhD in some field that's appropriate for engineering. So we try to set the bar at that. So.
Well, and like you talked about too, it sounds like a pedigree type thing from you're approaching clients as like, hey, we've got all the stable of PhDs and this type of method. So that makes sense from that perspective.
Yeah, but
I'm not too put off by that.
Okay. It can, depending on folks, it can be a little bit difficult for some folks. We are always looking for anybody who's got battery experience or who's got electronics experience. Obviously, in mechanical engineering, we approach and delve into a lot of different fields. So people who have mechanical PhDs, especially if they're listening to your program, they're probably pretty interdisciplinary. So, we'd like to hear from them.
Awesome. How do people get a hold of you? And like, if they've got a problem or if they want to talk about, the product, or generally, how do they get a hold of you?
Yeah. Probably the easiest way is just shoot me an email. So I'm sure you'll include in the show notes, but it's just Kreuzer@exponent.com. And you want to check the spelling on that because the last name's a little bit non-intuitive, but that's probably the best way. Other methods include LinkedIn. I try to be pretty active on there. It's a good opportunity to share ideas with the professional field. But
I was gonna say, if you follow Steve on Twitter, you're probably gonna get a lot more Sabres than you are Buffalo Sabres. We're both from Buffalo. He's much more of a sports fan than I am, but you'll get a little bit more Go Bills and Go Sabres than you will.
For no good reason, really. But
well, I was very luckily cured of my sports at a young age. I don't know what happened to you, man.
I don't know either. In a lot of ways, I don't know what happened.
Well, Steve, I am continually amazed that you and I keep crossing paths, and obviously we went to the same high school, the same college. We ended up in the same house, obviously, as roommates. But then now that we're in the same friggin' field too, it's like it's fate, buddy.
It is indeed.
And it sounds like you are doing some cool stuff. So I'm really glad you came on the show.
Yeah, thanks for having me. I appreciate it.
I had invited you. Hopefully, you will come to town for IMTS. You said you might or might not do that, but if you do, we'll hang out. I
think I
too.
might. It looks pretty awesome.
That's coming up in September. That's a machining show here in Chicago. If anyone else is going to that, let me know. And past guest, John Saunders will be there as well.
Nice.
So he's doing an event there. Okay, cool. Well, thanks, Steve. We'll talk to you soon.
Sounds good. Take care.